Yeah, so the exciting part about nuclear energy is when I started looking into it, I just was taken by how much we have, like on Earth. You know how much radioactive sources of energy that we have, and so this is one of my favorite lectures, is because it's just unbelievable how much energy is available in the nucleus. I think they rightly assessed it when they started exploring this. Of course, it was during World War II. They really started moving fast towards a nuclear bomb because they thought our enemies were working on a nuclear bomb. So it was a race to figure out, who would receive this or develop this technology first. But in reality, they were also thinking if we could control the chain reaction, we could produce energy that was so cheap we wouldn't even have to charge for it. Now, what are the things that are so cheap that we don't have to charge for? Well, oxygen. Okay, we not, it's not like oh, what was that really annoying Disney movie? Um, no, it was the Dr. Seuss Lorax. Yeah, it drove me nuts. Yeah. Corporations were so bad, and the government was so holy, and it was just, that's my rant on Lorax. But yeah, oxygen and even water to some respect. In some respects, we do pay a water bill, but you don't pay by the gallon until you go over a certain limit. So like the first, I don't know, 1,000 gallons or so are too cheap to charge for. They're charging you really for the infrastructure and not doling out, a gallon at a time. So there are things in our lives that at this point are really just too cheap to charge for, and electricity could be that way with nuclear power. So the downside is it would be so prolific that it would be hard to control the use of it as a bomb, right? So that's where the problem comes, that proliferation, because we're worried about using it as a bomb, we've severely restricted its use in terms of energy. So it's not because it's not able to be used for energy or that it's not safe for energy, but we're worried about it being so common and so everywhere that then some of it can disappear on the side and then be constructed into a devastating device. So it's that balancing act that we have. So this is a chart of the stability of the nuclei. Notice it's pretty flat through the middle range. Iron is right there in the middle. It's one of the most stable nuclei. If you wanted, I wish this chart really was upside down, because nature kind of rolls downhill, right, towards the most stable thing. But this is showing that the stability is uphill. But mentally, you should flip it so that if we split an atom, if we do fission, then we have over here this going from uranium-235, say, all the way down to lead. Notice we're going to a more stable nuclei. So essentially, we're going downhill. And this is the kind of energy we get from fission. And you can see why fusion is sort of our holy grail of energy, because look at the difference between hydrogen and helium. It puts fission to shame in terms of how much energy you get out. So per nucleus, you get, 8 or so more joules out of combining 2 hydrogens to make a helium than you do splitting a uranium atom. But this is the source of that binding energy. This also explains why you can split atoms and get energy, and why you can combine atoms and get energy, because it's not linear, right? There's a maximum in the middle. And so if you're a heavier atoms, you can split those and make more stable atoms. And if you're really light atoms, you can fuse them and get energy. This is also how we can tell the age of stars too. If stars are mostly hydrogen and helium, then they're very young. And you can look to see how much iron content you have from the atomic spectra in a star. And you can compare the ratios of certain elements, and you can kind of see how long it's been burning and fusing. So when a star is burning, the hydrogen is being fused into helium, and helium into other helium, and it just makes heavier and heavier elements. And so you can see that growth in the star. The star gets more and more dense, gets more and more hot, more and more pressure in the center of the star. Eventually it gets too unstable and it explodes. When a star explodes, you have all of those heavy elements that get blasted out, but all that mass is still attracted to each other by gravity, and so it will stop and kind of start coming back, and it will form planets, and solar systems. So you can have a star explode and destroy its planets and so on, and then it'll recoalesce and start to form another solar system. So that's what's been going on for eons in our universe and in our galaxy. So these masses of fission products, this is also an interesting thing. If you were to take the mass of the protons and the mass of the neutrons and try to build an atom, okay, so that'd be simple enough. We can look up the IUPAC, mass of a neutron and a proton and add all of those together to make an element or an isotope. And then if you look at the mass of that isotope, it's lighter. So it doesn't add up. There's a mass defect. And that's what that term is, the mass defect. You add up the protons and neutrons, and when you combine them and you look at the isotopic mass, it's lighter. And that missing mass is turned into energy. And that's what we mean by binding energy. So that missing mass is how much energy was released when those protons and neutrons came together. So we can actually tell by looking at the isotopic masses how stable each nucleus is. And that's how we got that plot on the previous page. So if we take two deuterium atoms, these are heavy hydrogen, so it's a hydrogen with a proton and a neutron, and we squeeze them together, really, really hard to do, but if you use a nuclear explosion to compress hydrogen, then you can get it to fuse. So think about how troublesome that is. We can't even do it with conventional explosives. You could take a hydrogen tank and surround it by plastic explosives and explode it, and it would squeeze the hydrogen, but it wouldn't get it close enough to fuse. But if you squeeze uranium together and create a nuclear device that creates fission type energy, that's enough to generate the pressure to fuse hydrogen. So we build this explosive train to take conventional explosives to create a fission device that then creates a thermonuclear or hydrogen bomb by squeezing the hydrogen. So if we can get hydrogen to form helium, it releases some gamma rays, and then it's also missing some mass. And so let's take the products minus reactants. So the mass of the helium-4, if we look the isotopic mass up, let's say in the CRC, it's 4.002602 grams per mole. So this is pretty easy to do. And then if we subtract the deuterium, I don't think that's... Yeah, there's a parentheses. Yeah, that's right. I was like, something happened here. Yeah, so 2 times the deuterium mass, okay, and that's the reactants, and the difference is this 0.024 grams per mole. So if we fused a mole, and that's a lot, if we fused a mole of deuterium to make a mole of 2 moles, a mole of deuterium molecule, and made a mole of helium, this is how much mass would be lost. And so then we can just take that mass and multiply by the speed of light squared, which again at 10 to the 8th squared, so 10 to the 16, we end up with 2.21 times 10 to the 12 joules per mole. That's crazy. So a mole of this deuterium is roughly 4 grams. And so if we multiply that by 4 grams per mole, it's 5.4 times 10 to the 11 joules per gram. If I want to take this and say it's 10 to the 2 times 10 to the 9, right? 9 and 2 is 11, okay? Then I can move this 10 to the 2 over here, and I can make this a giga. So that's where the gigajoules came from. So it's 548 gigajoules per gram. What the heck? That's a gram, not a ton. Those others, the chemical values, like a ton of oil is 45 gigajoules. A ton, that's 1,000,000 grams. And 29 gigajoules per million grams of oil or coal. And this is 548 billion joules per gram of hydrogen. That's unbelievable. Think about that. We can replace a ton of oil or a ton of coal with a gram of deuterium. I'm just sitting on that for a little bit, just so you can get your mind around what fusion can do for us. Yeah. In terms of comparing it to chemical explosives, like a ton of TNT, you'll hear the nuclear devices and so on. They're compared to kilotons or 1,000 tons of TNT, etc. This is what we're talking about. So, for the fission of uranium-235, it gives 2 times 10 to the 13 joules per mole. Okay, and so that's quite a bit. So we can use that. A ton of TNT gives off 4 gigajoules, and so this is 4 gigajoules per ton. If we take into account the mass of uranium-235, it's 85 gigajoules per gram. So if we multiply that by 1,000,000 grams, we would end up with 85 million billion joules per ton of uranium. Okay, so 1 gram is around 21 tons of TNT. So if you think about a chemical explosive, you see Hollywood, they blow up a car or blow up part of a building or something like that. I mean, those are pounds of explosives. They're not even tons. And yet a gram of uranium in just a fusion reactor would be equivalent to 21 tons of TNT. So that's about as much as a dollar bill weighs. So this is the strongest force that we know of, the nuclear force. It was determined, I guess, maybe if you remember back to your freshman chemistry class when they talked about the structure of the nucleus and Rutherford's alpha particles in gold foil. He shoots alpha particles through the gold foil, trying to see if there's any structure other than the electrons, and some of those alpha particles bounce back. And he said it looks like all the positive charge on the gold is held in a small spot, called a nucleus. So he came up with the term nucleus. He said because these alpha particles are such high energy, and the gold foil was hammered so thin that it was like shooting a howitzer, which is a big cannon, at the tissue paper and having the bullet ricochet, having that big artillery shell ricochet. That's how surprising the result was. And so he said something must be holding all of those protons together, which is crazy if you think about it, because protons repel each other. So it's kind of a dumb conclusion, except that's what the data says. The alpha particles bounced off of something hard. So something's holding these protons together. That was an unknown force at the time, so he just made it up. He said there must be a strong nuclear force that's holding the protons together. And it doesn't have a very long range. And so you've got to get the protons together against all that Coulombic repulsion. And it's almost like when they touch, they snap together and release that energy. So that's what's happening in fusion. We're trying to get those nuclei together so they touch. As soon as they touch, then they release that energy and make a new nucleus. I think of them less as grapes, like they always show a little cluster of grapes, and more like a water drop. So like water drops, they don't really do anything until they touch. But when they touch, they like snap together and change shape and release energy, right? Because they take a new shape. And so they're going to take a lower energy shape. And so that's the way I think of the nuclei, as a water drop or an oil drop. So we have a problem. This is 1945 when they're thinking about nuclear processes, and they think that the war's raging. They think maybe, the Germans were doing experiments with nuclear devices, and so were the Japanese. The British were working with us, and so this was the 1945 problem. And they built the nuclear device, the plutonium device. It was called the Fat Man because it was an implosion device, and it was surrounded by this big ball of explosives to squeeze the nuclear material. And they wanted to make sure that all their pressure gauges and cameras and everything were calibrated. And so out in the White Sands, New Mexico desert, they had to do a calibration test. And so they did 100 tons of TNT. So they got plastic composition B, plastic explosives in crates, and made this structure. And so that's what's being shown here, is that's 100 tons of TNT kind of in a big ball with a detonator in it. And they were going to blow that up and create a huge shock wave and measure their pressure gauges and everything so that they could measure the actual atomic device. This is 13 people across. So you can it's really grainy, but there's 13 people here in the group picture. So this is a huge thing. So yeah, we could make 100-ton TNT bomb, but we couldn't put it on a plane. So that's what, this effort. But here's, you can't put 100 tons of TNT on a plane, but you can put something 200 times more powerful on a plane. That's what the Trinity device looked like. You see, it's a big sphere, and inside that sphere is a sphere of explosives, and inside the explosive sphere is a sphere of plutonium. And so they squeezed the plutonium and made a critical mass, and it gave off 20,000 tons of TNT force. So, and you can see how big it is. This is, I think, is Ray Bradbury here. So that can easily fit on a plane. I say easily. The device with all the extra electronics and everything wouldn't actually fit in the bomb bay of the Enola Gay, but they modified the bomb bay. They had to modify the runway, so they had like a little pit, like a pit stop, like quick oil change pit, and they moved the plane over it, and they jacked this thing up. And once they got it, like the top half into the bomb bay, then the plane, it could clear the ground. But they couldn't get it under the plane without that pit. And so they put it in the pit, moved the plane over, jacked it up, strapped it in, and then away they went. So they could definitely lift it with the plane, but they couldn't actually fit it under the plane. They're much more smaller now. And now this is our current problem, the 2000s and Millennial problem. We are dealing with conventional explosives, and this was a Ryder truck. So you've seen like a panel truck, a Ryder truck, full of, they had 5 or 6 55-gallon drums of ammonium nitrate fuel oil. So you take ammonium nitrate fertilizer, mix it with diesel, and it will detonate, not just burn, because the nitrate has enough oxygen in it to help detonate. It doesn't have to wait for oxygen of the air to come in to burn the fuel. And so they mix the oxidizer in with the fuel. It's a pretty stable slurry. And then Timothy McVeigh and Terry Nichols put an explosive charge on top that detonated that truck. And this was in Oklahoma City. It was underneath the portico of the federal building, and you can see what it did. It took the whole front of the building off, but it didn't take the whole building down. So conventional explosives are somewhat limited in their power. I mean, this was a devastating attack, killed lots of people, destroyed the building, but it's not a nuclear device. So rogue nuclear devices are the things that we're worried about nowadays. For scale, you see these 2 chairs here? So this next image is about the same scale. So this is the Sedan crater, and you see that those chairs would fit easily on that observation deck, about the same scale. And that crater would be 25 city blocks. If you were to take that crater from the same altitude on Google Maps and go over to Oklahoma City and put it there, that would be 25 city blocks. Now, it wouldn't have been from a Ryder truck. It would have had to have been buried to create the crater, but still the devastation would have been equivalent to more than 25 city blocks because of all of the extra blast. This is just the size of the crater. The Sedan test in Nevada was actually engineered so that it would create the biggest crater possible. Like they analyzed what creates a good crater, because it was part of the Plowshares program, where they were trying to dig enormous holes, like maybe even canals, using nuclear weapons to save labor and so on. There's a downside to that, in that if you create a crater, then the device is buried pretty deep, and all of the radioactivity is captured by the dirt that's blown out. And so the place was incredibly radioactive. So yeah, we could dig a canal, but it would be so radioactive you couldn't go through it. You could send robots through it, but the soil and the dirt and everything that was blown out of the hole is sitting right there, and it would just be too radioactive. So the Plowshare program was kind of a failure in that respect. They could dig holes, but they couldn't go in them because it was so radioactive. A lot of the above ground tests, it was so hot and the air rises, the hot air rises, that it takes the radioactive gases and everything up into the upper atmosphere. And so it disperses it over an enormous volume. And so the radioactivity drops, it's measurable, but it's not lethal and not really even dangerous. But that's what an above ground blast gets you. Below ground, where it's completely contained, it stays down there below ground. The crater is the worst situation, where it actually breaks out of the top and sprays radioactivity everywhere. So bad bad deal. This was one that was an underwater test. This is the Crossroads Baker shot, and it was out in the Pacific after World War II. They were still doing research with these weapons, and just seeing, how they could control the yield. You see a lot of these in these blast photos and images, these little trails here. You see those things? I always wonder what those were. I got a bunch of videos on the nuclear testing times, and these are kind of like model rockets with pressure sensors on. So they shoot these off and disperse them in air, and then they blow up the weapon, and you can measure the pressure wave as it goes through the air. So that's what those little rocket trails are. So they shoot off these rockets, and then boom, they detonate the device, and you can see. And also they leave these marks in the little contrails. You can see the distortion of those contrails as it goes through the air. So video-wise, you can measure the shock wave through the air if you know where all those little marks. It's like tick marks in the air. So now in this, if you watch this, go online and search for Crossroads Baker shot or whatever, you'll see as this mushroom cloud of water climbs up, you'll see a dark image like this in the column, and that's a destroyer. Like the whole ship is flying in the air. Yeah, that's, just think of how powerful that is. It's crazy. 200,000 tons TNT equivalent. This could power 21,000 homes for a year. So, yeah. And it's released in just less than a second. All that energy, less than a second. So, this is a device. I can't tell you which one it is, but it was one of the ones at Pantex where I worked for 4 years between my last academic job and this one, working in the area of cleaning. So that's why my research is in cleaning, doing solvent substitution and procedural changes to how they clean the weapon. So it's kind of interesting. They knew that was my area of research and cleaning. And so they said, okay, have the person clean it. So he's got a little wipe, and like but we didn't clean the outside. But anyway, it was a funny picture. They're like, okay, clean something. So he got a little wipe. So that's Lonnie Cromer. Yeah. So this is what's going on with stimulated nuclear fission. I added that word. It's not in your notes, but I just wanted to emphasize some things. That's stimulated fission. You can have, spontaneous fission where the nucleus spits out an alpha particle or whatever, but this is where a neutron comes in. So we supply this in one way or another. It comes in, it hits the nucleus of uranium-235, and then it splits into a bunch of different possible products. So I've looked at sort of distributions of the daughter elements, and the only restriction is that they have to add up to 92 protons and 235 total nucleons. So there's not like a restriction that they have to be even. They could be pretty lopsided. Like you can see 36 and 56 or 40 and 52. Any two elements that add up to 92 protons are possible. You do see some peaks in there, but I looked at all the different ones and I couldn't really tell a trend. Maybe there is, and I just don't know it. I'm not a nuclear engineer, but if you wanted to just come up with fission products, you could just take that 92 and divide it into two parts and find what elements those are. And then you may want to look at the chart of the nuclides to figure out which of the isotopes are more stable so that you can figure out how the neutrons are split apart. But they don't have to be stable products. They can make really radioactive, unstable products. So if too many neutrons go towards one atom, then it's going to be a really crazy isotope of that atom and a really short half-life, and it's going to be super radioactive. So that's why that radioactive fuel is so hot when you first pull it out of the reactor, because it's got these crazy isotopes that are spitting out beta particles and alpha particles to try to get to a more stable isotope of some element. Now, this is a unique, well, not unique, but less common result in that you produce so many neutrons. Okay. They knew that they could stimulate fission in a lot of radioactive elements, but not all of those radioactive elements spit out extra neutrons. So that was a big search. In fact, Leo Szilard wrote kind of a speculative statement to saying, if we could find an element that gave more neutrons than it took, then we could sustain a chain reaction. So he didn't even know like which ones we might find, but he sort of set out the principle and said, if we look for a fission reaction that we can stimulate that produces a net gain in neutrons, then we can set up a spontaneous chain reaction. That chain reaction can be used in a slow manner for power generation, or it can be used in a fast manner for a bomb. It's the same mechanism. So let's see how we use these extra neutrons. So if that neutron comes in, and this is the chain reaction, you can see I've added that to the title. Neutron in, this is like the perfect situation, which is not realistic, but it's the best case scenario, that the first neutron hits a nucleus, that nucleus splits. Okay, we're not showing that here. We're just showing these extra 2 neutrons coming out, and those extra 2, it's like the original neutron and an extra one, hit 2 more nuclei. So you see it doubles, and then when those 2 neutrons come out, it doubles again. So you see this doubling each time. And you can take your calculator and you can hit, 1 times 2 equals, and then equals, and you can see how fast it grows. So every time it doubles, you get more and more energy. So if they can hold the device together long enough, they get more doublings. But yet it's releasing a lot of energy, so it wants to blow itself apart. So for a bomb, that's the trick, is holding it together to get more doublings. The more doublings you get, the bigger the boom. Okay. For energy, you want to control those neutrons. And so you let it burn. You might get not quite a doubling, but like a 1.8 or 1.7. It's more than 1. So you are generating energy and you're sustaining the chain reaction by controlling the neutrons. You can also control the neutrons by just having a small enough material. So our radioactive material upstairs, well, for one, it's not the type of material that would give 2 neutrons for 1 N. So it's not even suitable for fuel or for a bomb. It's natural uranium and americium. But we also don't have a critical mass. So if you look at this small mass on the left, it says subcritical mass. That notice how all 3 out of the 4 neutrons are escaping. Okay. So think about a crystal structure, and if you, let's see, what's the best visualization? Have you ever seen a picture of Arlington National Cemetery with all the crosses? It's like a crystal structure, right? If you've got a little small patch and you're standing like in the center, you can see lots of exit paths where you don't hit a cross. But if you're in the middle of this huge amount, there's no exit path where you're not going to hit a cross. You see that? And that's what we're talking about, a critical mass. If you have a small amount of mass, the neutron can find a way out where it doesn't hit a nucleus. But if you get more and more and more mass, there's more and more nuclei, and there's no path out where you won't hit a nucleus. So that's the concept of a critical mass or critical geometry. You could take a critical mass and put it in a geometry that's not critical, like stretch it out in a line. And then if somehow you could get that line to coil up, now you've made it to where there's nuclei all around and it couldn't go out. Now that's not a realistic design, but I don't want to tell you a realistic design. But if you stretched it out in a line, that would be subcritical. But if you coiled it up, that same mass would be critical mass. It's a critical geometry in that situation. And then if you also put it in a certain area where you could control those neutrons and maybe reflect those neutrons back in, you could have a criticality event. And that happens occasionally in industries that work with special nuclear material. There was one case where some people got irradiated pretty badly. They were working with uranium in a solution, and they had a subcritical mass if it was dispersed in the whole volume. And they were stirring it with a stir plate, and they turned the stir plate on too fast and created a vortex, and the powder went to the middle, and now it was a critical geometry, and they had a blue flash criticality event and irradiated themselves. Yeah, so they should never have been working with something that concentrated in the first place, because that was and so you have nuclear engineers that get in and sort of study criticality. What could we possibly do to create a criticality event? Let's stay away from that region, and they do a lot of modeling. This is the first nuclear pile reactor, which is a little crazy to think that it was in downtown Chicago at the University of Chicago. So they took graphite and they put uranium pellets in the graphite, and the graphite slowed the neutrons down so that they were right in the absorption window of the nuclei that they were going to hit. So these little pellets were subcritical. They put them in a geometry that was critical, and there's like a different absorption. You can think of like an absorption curve for the neutrons in terms of their speed. So it's more probable that they'll be absorbed by the nucleus or interact with the nucleus if they're slowed down a little bit. That's called moderation. So they use graphite moderators. And so these neutrons would go through the graphite, slow down, and then hit the next pellet right at the perfect speed to generate fission in the next pellet. And they built this thing up a layer at a time and measured with the Geiger counters. And they said Enrico Fermi was like rock solid on his theories. Like he was calculating the geometry of the next one, and with his slide rule, he would say, okay, the next flux should be X amount of, radioactivity measurements, and they would build the next pile, and an hour later they get it finished, and the needle moves up to exactly his number. And so it's very well understood, this process. So here's a sort of a modern reaction. This is the Chernobyl design. You all know about Chernobyl and its destructive, catastrophic explosion that they had. I read an analysis, like a book written on Chernobyl, talking about what happened, and it was dramatized pretty well by HBO in that special, and I would say they got the main facts right as to what happened, from that book that I read on Chernobyl, and then what they did in HBO. They had a couple of safety tests that they were going to get in trouble if they didn't complete, and so then they screwed up the safety tests. They let the reactor pretty much quench and go down, and then starting these reactors up is difficult. When you start the reactor, you pull the control rods out, and you get a burst of xenon gas, which is acting like a control rod. It's absorbing neutrons. And so until that xenon gas percolates out of there, it seems like the reactor is sluggish. It's kind of like an old car. You step on the gas, and it bogs down instead of going. But if you aren't careful in how you mash the accelerator, it can either go really high or it can die. Okay, and so they were fiddling around with that, and the dangerous design of these graphite moderated boiling water reactors is this thing called a positive void coefficient. So remember that the control rods are trying to slow the neutrons down and trying to absorb the neutrons, and they're using this water in those tubes to also control the neutrons. And if it gets too hot, you end up having boiling voids in here. So the little air pockets or cavities in that boiling water allow fast neutrons to go between the fuel elements. And we knew this was a bad design. We did use this design in the war effort to generate plutonium up in Hanford, Washington. But we, to my knowledge, never used this design for civilian power uses. So we knew it was a bad design. The war was on. We used it very carefully to make our nuclear fuel for the bomb program, and then decommissioned those reactors pretty quickly. And so we started making pressurized water reactors where you don't have these voids show up. So anyway, when people hear about Chernobyl and they say, oh, nuclear power is not safe, well, yeah, that reactor design is not safe, and we don't use that reactor design. So it's apples and oranges. You can't just say all nuclear power is just like Chernobyl. Okay. This is a pressurized liquid reactor. So this water loop over here, this is the primary loop. And when they say pressurized, it's above 100 C, but it's pressurized. So we're just further up on that curve. We're up in the liquid region where you can't it's not at equilibrium with the vapor. So there's no voids in here. We don't have a positive void coefficient or anything like that. We also don't have a graphite core. So the only thing keeping the control rods out is water. And so the control rods will never get stopped. That was the other thing in the Chernobyl thing with those exploding water lines and so on. It damaged the graphite core, and the control rods couldn't fit back down, so they couldn't actually stop the reaction. So it ran away and melted down. So we have this initial heat loop, and notice it's fully contained inside this dome. So the radioactive water and the radioactive fuel and everything are all inside this concrete and steel dome. So that's inside here, right, inside this area. There's a secondary loop where this water goes through a heat exchanger and flashes to steam, and that spins the turbine. So that's the second loop. And notice it's fully contained. So we're not even in contact with the second loop, and that's in this building. So this is first loop, second loop, and then after the generator, we still have a lot of steam, so we want to cool that water down so it can come back over here and pick up heat from the heat exchanger. And so then that's where the river or the lake or these external cooling towers are. And so if you see steam coming out of a cooling tower, it's this third loop that's generating the steam. Or if you have a big body of water, that body of water is not being pumped into the nuclear part of the reactor. It's the third heat loop. And so it's two partitions away from the radioactive material. The control rods, we like to have our control rods gravity fed, so they fall in from the top. So if the motors and everything fail, then gravity will draw them down and start to cool down the reaction. So then the primary circulating fluid goes through here and pulls all the heat that's generated. I don't know, it seems to me that we're still kind of in the steam era, even though our society doesn't appear to be steam driven. We're still using steam. We're using this nuclear reaction just to generate heat. And it seems like there's a better way that we just don't even know about. Think about the energy in those particles as they come out. They have an enormous, like mega electron volts of kinetic energy. And all we're doing is making them bang water around and make it hot. Now, maybe that's the most efficient thing. I don't know. But we're really not using the nuclear part to do anything. It's just hot. And that just seems weird to me. It seems like there's a technology there that we have not even imagined. Like, how could we possibly harvest the kinetic energy of those nuclei flying out? Yeah, so that's sometimes when I'm just daydreaming, I'm thinking, I wish there was a way, like we could, and the charges involved. These nuclei come out and they are stripped of their electrons. And so they are incredibly positively charged. You think that we could generate electricity directly with that. Like if we could make something that was, slightly radioactive, but super positive, then we've got a battery, like a really amazing battery, a nuclear battery. But I don't know how to split those charges and make them go through our circuit. So there's a lot of neat ideas there. Now we've known this for almost 100 years. So it's not like smart people haven't looked at it yet. But maybe you're the one, maybe you're the one that daydreams about this and looks through the literature and finds that, hey, this is a way to segregate those charges so that the negatives have to go through my circuit to get back to the nuclei and generate that kind of energy. We have a success story. I mean, ours is not the only nuclear navy, but it's the best, if you ask me. From 1948, when the first vessel was powered by nuclear energy, to today, we have 0 reactor core releases. We've put in 27 different nuclear power plant designs, over 210, and this is even growing even today, nuclear powered ships, 500 reactor cores, and so 27 different designs and 500 different reactor cores put into operation. and 5,400 years of operation. And we've gone over 128 million, probably double that now. This is kind of an older number. But this was the first all nuclear battle formation in 1964. So that's, some escort ships and obviously a carrier. It's pretty amazing that, like, now our submarines, the nuclear power plant that's put in that submarine will last the lifetime of the ship. So they don't even have to do refueling operations. So they build the nuclear power plant sealed up in its shielding, and they basically have water pipes coming in and out, and they weld those into the ship. And then when they're done, they drain the water out and, patch up the thing, and it's in its own waste container. So is it concentrated? Yes. Is it a substance that could cause harm? Yes, but it's controlled, so it's not pollution. So they just put those out in the desert of Nevada, and they sit there, and so it's in a controlled manner. It's stored. So that's the sort of the nuclear Navy is process. Now, resources are connected to the environment and to the energy that we get out of them. And so there's really nothing is zero impact. Nothing is zero emissions. There are noble gases that escape. We talk about radon coming out of the ground, nuclear processing and so on. You get krypton and some of these other fission byproducts that come out. And that's how we knew that North Korea had a nuclear program, because they were denying it, but we had a submarine offshore with a little sniffer sniffing for these radioactive noble gases, and they're like, yeah, a whole lot of krypton coming out of North Korea, and more than natural abundance, and so it's probably a fission reaction going on in one of these plants. So that was pretty interesting. So here's our total energy landscape in terms of exajoules, and now we can add uranium to it. So 9,000 exajoules of uranium that we have access to without reprocessing. So where did all this come from? Well, we've made a lot of nuclear fuel, but we've also made a lot of nuclear weapons. And so part of our drawdown from the 60s and 70s through the 80s, now to the 2000s, has been to reduce our nuclear stockpile. It's really expensive to maintain. And so even if we weren't just drawing it down through treaties, it would make sense to draw it down from the numbers that we had. And so we have all of this nuclear material that's probably one of our most valuable investments as a country, because it was expensive to produce. And now it's just sitting in storage. And so it would really be smart for us to start to convert some of this highly pure fissile material into nuclear energy. So it's not like we even have to dig it out of the ground right now. We could go for many years just using reprocessed fuel from our nuclear stockpile. In the, late 90s, they studied this. I believe Savannah River in Georgia, there was a nuclear plant there that received the contract to start converting some of this stockpile fuel, stockpile uranium and plutonium, into mixed oxide fuel for nuclear power pellets. Now, that World Energy Council produced this document that sort of showed the energy path going to 2100. And you can see that even though right now we don't really have a lot of solar, that's the one that I pointed out that had the most potential at 5 million exajoules. And that's per year. So, solar is the one that shows the most growth potential. But you can see coal is still there, but coal reaches a peak here in this decade, maybe the next, and then hopefully starts to taper off. Let's see, where's nuclear? Nuclear is pink. They're not real bully on nuclear, so I think that is a mistake. I think nuclear can really grow. We know how to do it. Our Navy proves that. So there's no problem, right? Well, there's no supply problem. We have plenty, but they're not shared, they're sold. They're distributed over the whole globe. And so we have this issue of economics and politics. So it's not an engineering problem. It's not a science problem. It's not a physics problem, but it's an economic problem and it's a political problem. Okay, so we've got to figure out, those problems are the mother of invention. Now, the pollution issue, again, we talk about focusing on control. At this point, we take our nuclear waste and vitrify it. So we melt it with glass or sand and make glass out of it, because then it's not going to leach out and go into the groundwater. So we make these glass ingots of long-lived nuclear waste elements, and we store the defense waste in the Waste Isolation Pilot Plant in Texas. It's a WIP site. You can Google that. We tried to open Yucca Mountain. We built these tunnels, concrete, isolated from the environment for earthquake, monitored for water, and so on. We've built these steel casks that we can put these glass rods in. We have them robotically monitored with Geiger counters and everything like that. But Congress still hasn't approved it to receive commercial waste. So commercial waste is still being stored at the nuclear power plants in those fuel pools. It's so hard for me to say that. In the fuel pools. And they're supposed to be temporarily stored there and then go to a permanent storage site. So right now we are kind of in a precarious situation because we haven't opened a permanent storage site for civilian power nuclear waste. So call your congressman, I guess. We're worried, some of the scientists are worried about this long-term storage of this waste in Yucca Mountain in steel containers, monitored, etc., when the real insult to the environment was from 1950s to the 80s when we were blowing up nuclear weapons in Nevada. This is the Nevada test site. You see all these little divots? Every one of those is a nuclear blast down in the ground with all of that nuclear waste just unencapsulated, just sitting there in the bedrock. Yeah. And so if there's going to be any groundwater leakage or anything like that, it's going to be right there in the test site. It's not going to come from Yucca Mountain. There was 828 nuclear detonations in the ground in the test sites. You can go there. Wikipedia has a great page on it. There's a new fancy page by the U.S. government on all the different facilities they have out there. We exploded almost 100 of them in the atmosphere in Nevada, about 90 miles from Las Vegas. It's kind of crazy. They said you could see the sky light up if they did one at night in Vegas. It's kind of weird to think about. So that's nuclear power, nuclear bombs, and nuclear waste.